Hello Q-steppers and fellow R-coders, and welcome to another tutorial in the series of How to in R. This tutorial is part 3 of multiple linear regression. We will cover the assumptions of multiple linear regression and what to do if we violate them. In this tutorial, we will cover how to check for functional form and heteroscedasticity. And we'll continue with normality and multicollinearity in the next tutorial. So why do we check these assumptions? It's very important to check these assumptions on our multiple linear regression model, and more important to fix them if we find violations. If we do not do this, then we cannot rely on the coefficients in our model, meaning we could produce false findings and interpretations. So we will start this tutorial where we left off on multiple linear regression part 1, where we had just run the model and were viewing the output. Now remember, multiple linear regression part 2 covers how to interpret those findings. So first we will cover how to check for functional form. If we have correct functional form, then this means that our predictors have a linear or non-linear relationship with the outcome variable. If this is violated, it means that our estimates in the model will be biased. So to check for functional form, we fit the model's residuals and the fitted values on a scatter plot. We then use the Ramsey reset test to check for functional form. If our p-value is under 0.05, then we conclude that we have violated the assumption of functional form. We can then remedy this by checking which variable or variables are problematic and transform them using the Box-Tidwell test. We can then run the model again with the transformed variables. Okay, so to check visually for functional form, we plot the residuals in a scatter plot on the y-axis. On the x-axis, we have the fitted values. We can then place a horizontal line at 0. This will let us illustrate on the plot if the local means are at 0. So going by this plot, we can see that the local means are roughly at 0 on the lower end, but not on the higher fitted values where they seem to fan out. So we may have violated functional form here. We can use the Ramsey reset test from the LM test package. Our alternative hypothesis here is that there is a difference in the amount of variance explained in the outcome variable, or in other words, we have violated the assumption of functional form. So this tests our model's fitted values to squared cubed fitted values. We use the reset test function. In the brackets, we place the model name. We specify which power to test. So this is the power of 2 to 3. Then we indicate that we are using fitted values. When we run that code, we see we have a p-value under the 0.05 confidence level. So we reject that null hypothesis and conclude that we have violated the assumption of correct functional form. We can check for problematic variables using the CR-plots function, which is short for component residual plots. So we load the car package, then use the CR plots with the model in the brackets. So let's run that code. On the plot, we are looking for the pink line to be linear with the blue dashed lines. Remember, our attainment variable was not statistically significant in the model, so we ignore that one. And we don't transform dummy variables, so we also ignore the urban variable. Looking at the pink lines, we don't have any variables that are way off, but let's go through the process for the income rate variable. and check if it should be transformed using the Box-Tidwell test. This will reveal if the variable should be transformed. So when using the Box-Tidwell test, we cannot input any negative values or values that contain 0. So as we have some data zones with 0% of people income deprived, we need to create a new variable with an added value of 1. To run the test, we use the Box-Tidwell argument. We then place the outcome variable followed by the tilde sign, then the new variable we have just created. We name the data set we are using, and then we add in na.action equals na.omit. This tells R to exclude any missing values. So this output shows the lambda score, the Z score, and your p-value. So it's under 0.05, therefore the variable should be raised to the power of the lambda value 1.2 in this case. So now we need to rerun the model, including the newly transformed variable. So now we need to rerun the model, including the newly transformed variable. Using the same code as above with a new model name, let's call it model 2. To add in the new variable, we include I to add the arithmetical operator. We name the original variable and indicate that we want to raise it to the power of 1.2. So we run the new specification model, and the summary we can see that our newly transformed variable has a p-value under 0.05. So if we run the CR plots again, we can now see that our transformed income rate variable has a more linear relationship with the outcome variable, meaning that we fix the violation of functional form. So let's move on to heteroscedasticity. So heteroscedasticity can be caused when our errors do not have constant variance. This means that our standard errors are smaller than they should be and can cause predictor variables to be significant when they actually aren't. So using the same plot we use to check for functional form, we can check for signs of heteroscedasticity. If there seems to be a pattern on the plot, we may have heteroscedasticity, but trying to define a pattern can be tricky. The pattern to detect heteroscedasticity is that as the fitted values increase, the residuals also increase. So from this plot, we see a decrease, then it spans out. So we may have violated the assumption of heteroscedasticity. So let's use the Bruce-Pagan test instead. So we use the BP test with the alternative hypothesis being we have heteroscedasticity. So we place the original model in the brackets and indicate that we don't want to use studentized residuals by adding the studentized equals false argument. When we run the code, we see we have a p-value under 0.05. Therefore, we reject the null hypothesis and conclude that we do have heteroscedasticity. To remedy this, we can rerun the model with robust standard errors. The code to do this is the CoF test from the sandwich package. So let's run the package. So we include the original model in the brackets, then specify that we are changing the covariance matrix to a covariance matrix with heteroscedasticity consistency with the VCOV equals VCOV HC argument. We run the model and we check if our predictors are still statistically significant, which they are, except for the attainment of variable, which never was significant. So as our predictors are still significant, we can have greater confidence that our previous results were correct. So the next tutorial will pick up from here and cover the assumptions of normality and multicollinarity. So happy coding, Q-steppers, and remember to subscribe to your social media channels, and thank you for watching.